Let's start our lecture. It's lecture number 6. We have already covered one half of this course. So we are supposed to know one half of this probability and statistics stuff. Okay, let's move on. First, I have to make a correction. It's a correction to the last example I gave you last time. Correction. Okay, if you look it up in your notes, the last example that we discussed last time, because I was in this great hurry, I didn't write correctly the formula. The probability density function is this. I forgot to put this pi here. Okay, well it should be this way, because if we don't include this pi, the integral from negative infinity to positive infinity of this will not be 1 as required. Okay, and second, well, I started this example by saying, suppose you have invented your own distribution. Well, actually, it's not easy to invent something really new. This distribution is not totally new. Well, actually, it's a particular case of the so-called student's t-distribution, which we are going to discuss, probably next time. All right, so much for this example and my mistake. Next, let me remind you that we are now in the process of discussing continuous random variables, and we talked about the uniform random variable. Another important example of this is exponential random variable. Well, I'll introduce it using an example. Well, suppose we're interested in the distribution of phone calls that arrive at a call center or at a service center. Calls arriving at a call center. Okay. Well, this, by the way, this is a kind of process that can be modeled quite accurately by the Poisson distribution with a certain lambda that we take from the statistics. So the number of calls that arrive per unit time can be described by the Poisson distribution with a certain value of lambda. But we can ask a different question, and it is really important in some applications. What is the distribution of the time that passes between two consecutive calls? Okay. So this is the time between two consecutive calls. Now, if the number of calls per unit time follows the Poisson distribution with mean lambda, then what is the distribution of the time that passes between two consecutive calls? Now, the big difference between the two variables is that a Poisson variable is discrete, and the distribution of this time is, this random variable is continuous. Well, I'm not trying to derive it. It's quite a long story. Let me just give you the formulas for you to get some idea of what it's about. Now, probability density function. Well, it's 0 if x, let's use t for the variable here to remind us that it's about time. So it's 0 if t is less than 0, and that it's lambda e minus lambda t for any t that is greater than or equal to 0. Okay. Well, now generally, it looks like this. Okay. Now this y-intercept, the coordinate on the vertical axis where this curve starts is actually equal to lambda. Okay. Lambda. Well, so lambda can be, well, any number. If it's, for example, if it's 1, and suppose this is 2, for example, okay, and lambda is 1 here. Now, if lambda is a smaller number, then it starts at a smaller coordinate, y coordinate here, but it's more spread out. If lambda is a larger number, then the beginning value here is larger, but then the curve goes down and approaches the x-axis in a steeper way, more rapidly, okay, like this. Well, we can also write the cumulative distribution function. It's a very simple business. You can integrate this. Let's not spend time on this. If you have reasons to use this distribution, to be interested in it, you can easily find these formulas. What is really interesting about this distribution is this. Okay, memoryless property, memoryless, from the word memory. Memoryless. What does this mean? The probability that okay, let's try to understand what's written here. Now, let's look at the right-hand side. T capital stands for the random variable, the exponential random variable. And this is the probability that the random variable takes on a value. And let me remind you that T capital is the time between two consecutive calls. It's the probability that T capital takes on a value greater than a certain given little t, certain specified t. And the left-hand side is this. The probability that T capital takes on a value greater than little t plus little s, given that vertical line, given that it's greater than little s. Okay, now this is the conditional probability that we will have to wait at least t units of time, given that we have already waited s units. And this is the unconditional probability that we'll have to wait for the next call at least t units starting from the 0 point in time. Now, if you think of it, if you try to understand what it means that the process kind of starts anew at every point. And what happened before it doesn't matter, okay? Whether the probability distribution is started anew at every point in time. This is a loose way to describe it. I mentioned this property because actually it arises in various applications of probability theory, and it relates not only to this random variable but to some other models too. Okay, so much for exponential distribution. The next big chapter in this course is the normal distribution, which is really important. Well, if somebody asks me what is the most important stuff in this whole course, what are the most important probability distributions, the question will probably be among the discrete distributions, it's the binomial distribution, and among the continuous distributions, it's the normal distribution. And what's more, they are not very different actually, okay? And this is what we are going to discuss now. Okay, so the big title here is the normal random variables. But before we actually talk about this, we'll mention this. So suppose we look at a binomial random variable with a probability of success on a particular Bernoulli trial equal to P and n trials. Okay. Well, sometime earlier I stated that the expectation, and again, let me remind you that this Greek letter mu, well, not a very good representation of this letter. I'm using my hand to erase it. Well, maybe this is a bit better. So E capital and mu, I use as synonyms here. So for such a random variable that actually results from n Bernoulli trials performed in a row, the expectation is n times p, and the variance is equal to n times p times q. Okay, so this is what we know. But then sometime in the 18th century, in the second half of the 18th century, well, a certain mathematician, and the name was Moivre. Okay, I'm not sure this is a good French pronunciation of this, but well, this is the best I can do. So Moivre, notice that when the number of trials, when n increases indefinitely, goes to infinity, this distribution takes on a certain very regular shape that in a sense reproduces itself, that never really changes when n increases further and further. Okay, so there is a certain limiting distribution. Before we actually state this distribution, write the formulas and plot a graph, let's ask this simple question. What's the maximum, the most likely value? Here we perform n Bernoulli trials with the same probability P of success on each trial. And X stands for the number of successes we get on n trials. What's the most likely number of successes that we get on n trials? Most likely number of successes. Well, actually, this gives us an idea of what we should expect, n times p. But n times p doesn't have to be an integer. If n times p is an integer, then it's the right answer. The most likely number of successes is just this. But n times p may be a fractional number, then the most likely number of successes is one of the two neighboring integers. Okay? Well, let's let's draw this graph. We represent the probability of every possible value in this random variable by a vertical bar or line. Okay. So, if n times p is an integer, then it's one of the possible values. Okay. Then then this is the highest bar in this chart, in this diagram. And then if we depart from n times p to the right or to the left, these probabilities decrease, fall down to 0. Okay? Well, and if we draw a curve through the tips of these bars, we get a certain curve, a certain shape like this. It's commonly called bell-shaped curve. Now, this is exactly what was noticed. When n increases, this bell-shaped curve actually remains itself, but it's not placed at some fixed position on the line. When n increases, n times p increases proportional to n. And n times p can be thought of as the center of this distribution. So the center of this distribution shifts to the right on the horizontal axis as n increases. This is one thing that happens when n increases. And another thing is that as n increases, the distribution becomes more spread out. Look at this. Variance increases as n increases, okay? So two things happen when n increases. This bell-shaped curve moves to the right proportional to n, and it spreads out proportional to variance is n times p times q, so sigma is square root. Okay, we talked last time about sigma being the right measure of spread, not variance in practical terms. So the spread increases proportional to square root of n. All right, and now it's time to actually define the normal distribution, which is the limiting case of binomial. Okay, so Moir and then Laplace studied this limit, the limiting case of binomial distribution. And they formulated this remarkable law. So normal distribution and this is the standard, the accepted notation for it on capital, and then we state two parameters, mu, which is the expected value, and sigma squared, which is variance. Okay. Well, and okay. Well, this is. Let me draw a picture here. Well, not a very good picture because it must be symmetric. Well, maybe this is an approximation to symmetry. All right, look at this formula. What stands before this exponential is just a scaling factor. It's just a constant that is needed to make the integral from negative infinity to positive infinity equal to 1, which is the necessary requirement. Then the actual function, the variable part, is this exponential thing. And look at this exponential. What is variable about it, again, is x minus mu squared, okay? So it's the value taken on by the variable minus mu, which makes it the deviation from the expected value. Well, if this is mu and this is x, then this is the deviation, and it's squared and divided by a certain constant, again, to make it consistent. So the actual law, the variable thing about this law is e raised to the power minus x minus mu squared, okay, plus some constant factors. Now, what kind of law is this? Because we have a negative sign here. Well, this exponential is never larger. Well, this whole thing is never larger than 1, and it takes the value of 1 when x equals mu. That is at this point here. Okay. Well, considering this this constant factor here, the largest value the maximum of this function is just this. Okay? And it's attained at the point mu. When x moves to the right or to the left from mu, x minus mu squared becomes positive, and including this minus, we conclude that this exponential is less than 1. So we have a decreasing. If we shift from mu to the right or to the left, the value of the function is decreasing, always remaining positive, which is a necessary requirement for any probability density function. Okay, so I'm trying to explain that although this formula looks a bit difficult to interpret, actually the essential things about this formula are not so very difficult to understand. Because of this exponential, because of this minus, and because of this square, we have this law. When we go to the right or to the left, depart from the right to the right or to the left from mu, the function falls down to 0. Okay. Now, how quickly does it fall down? The answer depends on the value of sigma here. Okay. If sigma is a small number, then this value here becomes large very quickly, and this function falls down to 0 quite quickly. On the other hand, with a large sigma, it's more spread out. This is my attempt to make some meaningful, intuitive conclusions from this formula. Okay. Well, okay. Now, look at this. This formula includes two parameters, mu and sigma. So we are not talking about just one unique random variable that is called the random variable. Rather, we have an infinite family of random variables that are called normal random variables. And this is a two-parameter family. So it's a two-parameter family of normal random variables. Okay? This is observation number 1. But a much more important observation is this. Actually, this infinite set, the various normal distributions in this two-parameter family are not really very different. Actually, they all can be converted into just one random variable. And this is how it's done. Conversion of a normal random variable into the standard normal random variable. All right, what do we mean by this? First, now it was noticed, actually it can be proved quite rigorously using this formula, that if we look specifically at the probability that x gets within the interval from mu minus sigma to mu plus sigma, so in this interval, and this probability is represented by this area on the graph. Again, we look at the probability that the normally distributed random variable with a certain value of mu, a certain value of sigma, gets within the interval from mu minus sigma to mu plus sigma. It turns out that for any normal random variable, that is a normal random variable with any value of mu and any value of sigma, this probability is just a constant number. Let's write it here. Mu minus sigma mu plus sigma is equal to 0.682. Okay. Also, we can look at a larger interval, mu minus 2 sigma here and mu plus 2 sigma here. And again, the probability that x gets within this larger interval is equal to okay, 0.9554. And if we look at a still larger interval, mu minus 3 sigma look at this number, 0.997, which means that mu minus 3 sigma and okay, mu plus 3 sigma here. So this, let's use this kind of shading. So almost all, well, if we can put it this way, almost all the probability is associated with this interval, mu minus 3 sigma to mu plus 3 sigma. 0.997 out of 1 are contained in this, or are associated, is associated with this interval. Okay? Now, what's important to understand here is that these formulas and these numbers, these exact numbers, relate to any normal distribution, not just one particular distribution. Which leads us to the guess that actually we don't have to use this difficult formula. We can use, well, in practice, when we use the normal distributions to model various processes, we have to deal with normal distributions with any values of mu and sigma. But these relations leads us to understand that actually we can use just one standard normal distribution to answer all the questions that relate to any normal distribution, whatever. All right, and this is what we do in terms of this conversion. So suppose x is normal with mean mu and variance sigma squared, then well, actually this statement deserves to be called a theorem. It's important. Then x minus mu over sigma is actually normal with mu 0 and sigma 1. Now what is this standard normal distribution about? So there is a name for it, z. This is a special name, z, reserved for the standard normal distribution. And PDF, so this is called standard normal. PDF is 1 over 2 square root 2 times pi e to the power minus z squared over 2. Okay? And well, the graph is very similar to the general case of the normal distribution, but the characteristic feature is that it's centered about 0. Okay, mu is 0, and because sigma is 1, this highest point here is this. Okay, and it's again a bell-shaped curve. It falls down to 0 as we move away from 0 to the right or to the left. Okay, Now, what's the special interest? What is the special importance of this random variable, this normal random variable among the infinitely many normal random variables? Now, it's this. Well, the cumulative distribution function so phi, little phi is defined. I'm sorry, I didn't write any name here. The typical, the accepted name for this PDF function is phi, little phi. Okay, and accordingly, the integral, the cumulative distribution function is called capital Phi. Well, I'm not sure these names are universally used, but they're pretty common. All right, and now again, the main idea, this is just preliminary work. The main idea is this: if x is normal with mean mu and variance sigma squared, and z is the standard normal as defined here, then f capital, which is the cumulative distribution for this normal of general type, computed for some given value of x, is just equal to phi for z, where z is equal to x minus mu over sigma. Okay, which means that we don't need to deal with all these infinitely many different cumulative distribution functions. We only need one of them. We need to study carefully and have detailed information on this. And if we have this, we can answer any questions about any normal distributions. Okay? And this is how it's actually done in practice. Well, at least this is how it was done before the computers arrived. Now the computers can answer any questions that you ask. All right. Now, okay, you can say, all right, this is good to know. It's good to know that any question about concerning any normal random variable can be answered using the standard normal. But how do we know? Do we really know this? What is this phi capital? I only wrote little phi, which is the PDF function. And if you followed me closely, you might have noticed that I didn't attempt to write a formula for the cumulative function. And it's not an accident. Actually, this function is not integrated in elementary functions. There is no way I can write the integral of this in closed form. Okay? So this is a difficulty. And because it's not reducible to any elementary functions, well, again, before the arrival of computers, the approach that was universally used by statisticians and economists and engineers was using tables. So in any statistics textbook, if you look at the back, you'll find a table for the standard normal distribution. And actually, you're going to use tables of this kind on this course too when you do practices. All right, let's write it this way. So for the standard, we can sometimes in some books you can find this function tabulated, just the way it's written here. But there is something that can be made use of, that can be used to make a table shorter and maybe a bit easier to use. I'm not sure about easier to use, but shorter is right. Now we can use symmetry symmetry. And the symmetry is this. Look at this phi function. It's symmetric about 0. Well, the right word to use, it's even. So phi of z is an even function. And this can be used to make the table shorter. This is how it's done. So phi of z, which is the integral from negative infinity to z of phi of little phi, we can split this into this sum minus infinity to 0 plus integral from 0 to z phi of. Okay. Now, and because phi, little phi here, is an even function, and because the integral from negative infinity to positive infinity of this is 1, this integral here is just 1/2 of 1 of 1. That is 1/2. Okay. And let's introduce a special name for this other integral. Let's call it phi capital 0 of z. Okay. Phi of z is just cumulative distribution function, and let's call one piece of it phi 0. Then let's continue here. Then we have 1/2 plus phi 0 of this. Okay. Now what's the point in these manipulations? The point is that we can tabulate phi 0 instead of this big phi function. Okay. And phi 0 is 1/2 of it. It makes the table shorter. Okay, now because little phi is even, phi 0 is odd. So when tables were widely used and well, it was something that was used on the regular basis. When it's enough to develop a table for positive values of z alone, and then if we need a value for negative z, we can use this formula that says that phi 0 is an odd function. All right, let's give it an example. Well, suppose you conduct a survey you conduct a field survey aimed at developing a probability distribution for the total price of the purchases that a customer makes at a supermarket. Okay, so a person arrives at a supermarket and buys things like, well, bread, milk, meat, vegetables, whatever, and the objective of your survey is to develop a distribution for the total price or worth of these purchases. So total worth of purchases of an individual at a supermarket. Okay, let's denote it by X. Well, suppose your findings are, first, that this variable can be modeled by a normal, that a normal law can reasonably be applied here. So X is normal. Normal. Okay, this is your finding, or maybe it's your assumption. Also, after some field work, you find these estimates for mu and sigma. Let's say Well, I'm not accustomed to this symbol, and I'm not sure you're accustomed either, but this is ruble, okay? And mu is 350 rubles, and sigma is 105 rubles. Good. So we deal with a random variable that is normally distributed with mu equal to 350 and sigma equal to 105. Suppose the company that contracted you to carry out this research is interested in the extremes. What proportion of all the people buy very little, and what proportion of all the customers buy a lot? Okay. Let's answer some specific questions. Question A. What's the probability? Well, what's the probability that a randomly chosen customer in this supermarket buys stuff to the total worth that is less than 250? Okay. Looking at this number, mu is 350, and it's a normal distribution which is essentially symmetric about mu. We can say straight away that this answer must be less than 1/2, okay? But I'm afraid we are not ready to give any more accurate answer. All right. Now this is how it's worked. Rather than trying to work in terms of x, we work in terms of z. So we convert this problem into a problem about z, which is the standard normal. And z is 250, which is the given value of x, minus mu, which is 350, and we divide it by 105, and the answer here is negative, is this, okay? So if we try to plot it, mu equals 350, and this is 250. Now we are talking about the probability associated with this left tail, okay, associated with the values of x that lie to the left of 250, this left tail. So this is the question here. All right, and how do we find the answer? This probability equals to 1/2 plus phi 0, and we substitute this value for z, minus, okay, like this. But we are not quite ready to use the table, because the typical table doesn't contain any negative entries for z, okay? To be able to use the table, we need to use the property of oddness of this function, and rewrite it this way, minus phi 0, okay? So the argument z is positive now, but we have a minus that stands in front of it, okay? And now we are ready to look it up in the table, and this is the answer. So the probability that a randomly chosen customer in this supermarket buys stuff to a total worth less than this is 0.17. Okay, as I promised, it's less than 1/2, but again, my intuition is not good enough to provide a really accurate answer for this. All right, let's ask another question here. What's the probability that x is greater than is greater than 500? Okay. So now it's about this tail. If this is 500, we are talking about this tail. Okay. Of course, it's less than 1/2, certainly. And, well, we can do a little better than that. Because the distance between the mean and 250 is less than the distance between 500 and mu. Okay? This tail is smaller than the first tail. Okay? So we can expect that the probability associated with this right tail is less than this one. All right, how do we compute it? Again, we convert x into z. So it's 500 minus 350 and divided by 105, and this is 1.43. Okay, so the probability is equal to, and now we write this. It's look at this. It's 1 minus phi 1 this. Okay. Well, everything that lies to the left of this point from negative infinity to this point is the cumulative distribution function, phi capital. But we do not work with phi. Instead, we work with 1/2 of phi, which is phi 0. So instead of this, we write, and here we substitute 1/2 plus 4. Okay. This is substituted for phi here, and as a result we have this formula. Okay, and using the table, this is what we get. Let's ask another question. As I promised, it's less than this first answer. Let's ask another question. Here we are going to use the same table in reverse. And the question is this: find x such that, and this is what we want. Okay, so we want to identify such a value of x on the line that the probability associated with all the values to the left of it is equal to 0.8. Okay, so in the first two parts of this example, we found certain probabilities given specific values of x. Here it's the other way around. We want to find x given a probability. Okay. Now, if you studied any kind of statistics, such as economic or social statistics, you certainly encountered this concept. It's called percentile. Is it familiar? So this is called 80th percentile. Okay, actually, and again we can use the table. Let's not go into details here. Let me just give you an answer. With this value of x, which is 438, okay? Now, the probability that this normal random variable takes on a value that lies to the left of this is 0.8, okay? So if you repeat this experiment again and again, 80% of the time, the value of x will lie to the left of it. All right, now let's return to the question of the normal distribution being the limiting case of binomial. Okay, so normal as approximation to binomial. Okay. Well, let's discuss an example. Let's consider this binomial distribution p equal to 0.4 and n equal to 30. We want to see whether with this number of trials, 30, that doesn't look very large, okay? It's not 3,000 or 3 million, just 30. Whether for this number of trials, the normal distribution is a good approximation to the binomial, okay? Now, before we, first, let's ask this specific question. What's the probability that the number of successes, or in terms of the random variable, what's the probability that the value of this discrete random variable is between 10 and 20 inclusive, okay, including the extreme values. And using the binomial distribution, we get this exact answer. So this is obtained from the binomial distribution. On the other hand, we can compare this binomial distribution to a certain normal distribution. And the normal distribution here is has mu equal to n times p, which is 30 times 0.4, which is 12. And sigma is square root of n times p times q, that is 30, 0.4 and 0.6, and the value of this is 2.683, okay, like this. So we compare this binomial with this normal, and we want to see whether the normal here is a good approximation to the binomial. Let's compute the same probability using the binomial now, okay? And this probability is okay, look at this. Is it a good approximation to this one? Not really, okay? It's kind of ballpark figure. It's not very different, but it's not very close either, okay? Actually, we can do better than this. Look at this. Well, let these k minus 1, k plus 1, let these be 3 consecutive values in the binomial distribution. Okay, and this is an approximating normal. Question: what should be associated with the sum of these 3 binomial probabilities? Should be associated with the area under this curve between k minus 1 and k plus 1, for example. Well, if you think of it, not quite. A better idea is to include 1/2 here and 1/2 here, okay? Well, this is, if you look at the bigger picture, if you look at this entire distribution, now you need to add 1/2 to the leftmost number value and 1/2 to the rightmost value for these two distributions to match, to be consistent. All right, I really don't have time to go into this any further, but let me just tell you that if we do this, this is called continuity correction. Continuity correction. So, and if we use this, apply this continuity correction, we should not use 10.5 instead of 10 here. So it's 10.5, and it must be 20.5 for this other extreme value, and then the answer is okay. Now, if you compare this answer and this answer, you'll see that this one is correct to 2 decimal places, which is a very good match in practical terms. Okay, so it's an important example. I hope it'll leave a trace in your memory. Well, even for a relatively small number of trials, 30 is not a large number of trials, the binomial distribution can be quite closely approximated by the corresponding corresponding normal if we use this continuity correction. And actually this is how it was done in practice. Before computers arrived, engineers and scientists and economists used tables of binomial distribution, which are quite bulky and very difficult to use and quite a bore. Because it's so tedious to use the actual binomial distribution, the normal approximation was used on the regular basis, and this is how it worked. All right. Now, this said, let's talk a bit now. Let me tell you that the normal distribution is the most widely used distribution when some processes are modeled in economics, for example. But it's not really universal. Sometimes it's not a good choice. Okay. Let's call it limitations of normal distribution. Limitations. So it's not always a good idea to use the normal distribution to model the random variable that you have to deal with. So a normal distribution is not an appropriate choice if so let's write it this way, not appropriate if first, if the random variable under study is essentially positive, well, a comment is necessary here. The normal distribution, by definition, extends from negative infinity to positive infinity. The set of positive possible values for it is just a set of real numbers. On the one hand, so you might think that it's absolutely unacceptable for modeling the random variables that are essentially positive, such as, for example, the body weight. It can't possibly be negative, okay? And the random variable admits negative values. On the one hand, it's true. On the other hand, if, for example, if the average weight, I have no idea what the average weight of say, population in Moscow is, but suppose it's, well, 75 kilograms. It's just a wild guess. Suppose it's 75 kilograms, and suppose sigma is something like, again, I don't know, something like 5, okay, or even 10. Then I want you to appreciate this. The normal distribution admits negative values, but if you deal with a normal random variable with mean 75 and sigma 10, the probability of any negative value will be absolutely negligible. It will be so small that it can be and should be neglected, okay? So on the one hand, it's kind of contradiction if we try to use the normal random variable to model a certain random variable, physical random variable that doesn't have positive values. But on the other hand, the probability of these extremes is so small that it can be neglected in many cases, but not always. So when we say this, if the random variable that you need to model is positive, it doesn't always mean that the normal random variable can't be used. But if the probability of this negative tail cannot be neglected, then the normal random variable is not a good choice. Okay? And second, well, the random variable that you study can be heavily skewed. Heavily skewed. Now, what is skew? What is skewed? Skewed means non-symmetric. Non-symmetric. So the normal distribution is essentially symmetric. And when the random variable that you study is essentially non-symmetric, then you should not look for an appropriate model among the normal random variables. By the way, it's a known fact that the body weight of an individual is a random variable that is rather strongly skewed, and the normal random variable is not a good choice for modeling this. All right, and sometimes outliers are important. What is an outlier? Outlier is a value that is a long distance away from the mean. Well, if we accept the normal random variable model, we should treat these extreme values as negligible. The probability associated with any of them is just zero or almost zero. On the other hand, there are some random variables, there are some processes and situations when these outliers should not be neglected. Well, I've been thinking of a convincing example for you. Well, I'm not sure I've come up with a good example, but well, this is an example that I have for you now is this. Suppose you conduct a survey on the amount of reading that young people do. Okay, people of your age. How much does a randomly chosen young person read per month or per year? Okay? Well, it's my impression that young people today read much less than young people in my time. Okay? Maybe there is a lot of competition from computers and other media. I don't know. Well, suppose you come up with these figures that the average amount of pages that an individual, a young person reads per month is, what is a realistic figure? I don't mean any stuff related to your studies, to your education, just something, well, fiction. Tolstoy, Dostoevsky, things like that. Suppose you find that the average number is 15 pages. Is it a realistic number? Well, maybe it is. Somebody reads nothing at all, and somebody reads twice more. Okay, and you try to apply to model this distribution using the normal law, but then you notice that although this is a true average number, 15 pages per month, some young people read a lot. Okay, so this general depressing picture of well, reduced amounts of reduced readership. The general picture has, well, it's not quite as simple as that. Okay, young people in general read rather little, but some of them read a lot, maybe more than young people in my time. And these intellectuals, these intellectual young people may be few in number, but it would be a great mistake, if you ask me, it would be a great mistake to neglect them. Okay? Because maybe this is something very important. The proportion that they make in the whole generation is maybe small, but it doesn't mean that we should neglect them. Maybe it's something very important happening here. Do you understand what I mean to say? Sometimes outliers should not be neglected. It's something important going on here. Okay. All right. Now next section. Okay, combinations of random variables. All right, suppose x and y are random variables. And these random variables are associated with the same sample space. So it's the same sample space. Sample space. Well, if you remember, this is the notation we used for a sample space. And when we first introduced random variables, we said that actually the underlying thing is a sample space. And we define a random variable as a function on the set of possible outcomes. Suppose two such functions are defined on the same sample space. Okay? How can we describe their joint distribution? So, joint. Okay? What is the joint distribution? Well, I limit this discussion to the case of discrete random variables, and the case of continuous random variables is pretty similar, but then we'll have integrals instead of sums, and that's it. So, the basic thing is this. Okay? Now, xi here stands for the possible value in the variable x. And if I runs through all possible values, then x runs through all possible values, all the values that is possible for this random variable. And y sub I is a possible value in the y random variable. Okay, what's written here is this. The probability that x takes on the value xi and y takes on the value y sub I, okay? And we define denoted by p sub I j, okay? It looks simple enough, okay? But a lot of derivations are made from this. Now, this said, we can ask this question: what's the probability of a particular value of x if we let y take on any value, okay? And this is called marginal probability. Actually, it's essentially the same thing as total probability formula. If you remember, at one of the lectures, I introduced this total, I think it was lecture number 2. It was the total probability formula. And let me just remind you that we talked about a partition and a specific event that we're interested in. And the probability of this event, given a partition, can be computed as the sum of the probabilities into which the probability of this event splits by this partition. Okay, when I try to explain it in words, it sounds rather vague, but you can look it up in your notes. Well, basically, what we are doing here is just the same thing, total probability formula. And then we write this. Look at this. If we sum up these probabilities p sub ij over all the possible values that j can take on. In other words, if we sum up over all the values that y can take on, what we get is this total probability for p, or the accepted name in this section is marginal probability. And in the same way, if we sum up over this other index, what we get as a result is the marginal probability for this y random variable taking on a value y sub I. All right. Now, why do we need this stuff? Well, actually, it's the very beginning of a very long story, because as the study of joint distributions of random variables is a very huge topic. But for the purposes of our limited course, what we really need is this theorem. Now look at this: x plus y. Suppose x and y are random variables defined on the same sample space. What's this expected value of x plus y? Well, we have this remarkable formula. Okay, I'm sorry, it's not very well written. I'm sorry about this. For one thing, square brackets are accepted in this formula, and it's like this. It's like this. Wow, I'm doing a poor job of it. Okay, so the expectation of the sum of two random variables is equal to the sum of the respective expectations, which looks so simple that you might think that it's obvious. Actually, it's not, considering that there may be a dependence between the two. Okay, there may be a dependence, and the real meaning of this formula is that it's true even for random variables that are dependent on each other. So it's something unexpected and not at all trivial. Okay, and B here, well, if we consider the random variable that is given x times a constant, then it's like this. Okay, let's give it an example. It's a very interesting example, and also it's important in certain applications. Example. Well, suppose n letters have been typed, and the envelopes have been prepared for them, with envelopes with the right addresses typed on them. So we have n letters and n envelopes that correspond to these letters. But then the careless secretary mixed up all the letters and envelopes, and as a result, the letters got inserted into the envelopes at random. So n letters and n envelopes. So they are inserted at random. Now, what's the expected value of the letters that get into the right envelopes? Okay. So let's define the variable y as the number of letters that get in the right envelopes. Okay. Now, a very elegant solution to this is given by this reasoning. Let's present y as the sum x1 plus x2 up to xn, where x1 is defined to be x1 is 0 if the first letter gets into the right envelope, 0 if the first letter gets in the right envelope, and 0 otherwise. Okay, this is the definition. Well, I'm not sure you can read this, but let me read it again, and I'm trying to explain this. So we associate a separate random variable with each letter, and this random variable is defined in this way. x1 is, by definition, is 1 if the first letter gets in the right envelope, and it's 0 if it gets in the wrong envelope. And the same for the second letter, the third letter, and so on. Okay? Now, do you understand that y, the total number of letters that get in the right envelopes, is the sum of these? Do you understand this point? Okay. Now, the next question is this. Are these random variables dependent on one another or not? Well, obviously they are dependent, because if we know that x1 gets in the right envelope, that changes the situation for the other letters. Okay, they are physically dependent on each other. All right, and although they are dependent on each other, the expected value for y must be equal to the sum of the expected values for these individual random variables. And what's the expected value of x1, for example? Now, if the letters are inserted in the envelopes at random, then what's the probability that the first letter gets into the right envelope? It's 1/n. Okay? So 1/n times 1 plus n minus 1 over n times 0. The expectation of x1 is 1 over n. Are you following this? And this applies to each term in this sum. So the expectation of each individual random variable is 1 over n. And we sum up n terms like this, which gives us this answer. The expected value of letters that find themselves in the right envelopes is 1. A very interesting answer, and it's not only interesting, it's an important probabilistic model in some applications. All right, and again, this is not a trivial result because these random variables depend on each other. All right, if they are independent, we have something to say about the variances too. So this was about expectations. So for independent random variable, what is this? What does this mean? What do we define as independent random variables? So this is what we start with, the joint distribution, and we use this notation, but we also but sometimes for some random variables, the probability in this joint distribution is always equal to the product of the respective marginal probabilities. So these are marginal, okay? And marginal probabilities were defined just a bit earlier. Well, actually, this is easy to understand or easy to accept, because this is how we defined independence for events. Before we even started talking about random variables, we talk about independence of events, and the definition was this: the probability of the joint event is equal to the product of the two individual probabilities. This is similar, and this is actually not a different thing. So theorem: if x and y are independent random variables, then A, the variance of x plus y equals variance of x plus variance of y. Okay, B, variance equals c squared over variance of x. All right, independence is necessary here in part A. Okay, in part 2 we don't have two different random variables, so independence is not relevant. But for the first part here, we need to assume that x and y are independent, otherwise it's not true. And if two random variables are independent, then the variance of the sum is just equal to the sum of the individual variances, which is a very important question. Okay? Well, why? Let me give you an example of how random variables are dependent. Okay? For example, well, some time ago we introduced the uniform random variable, this type of random variable called uniform random variable, and the example that I provided was the waiting time till the next train arrives in the underground. Okay? But if you think of it, we can consider two random variables here. One is the waiting time to the next train, and the other the time since the last train left the platform. Okay? Both are random variables, and let me tell you that both are uniformly distributed. Actually, they have the same uniform distribution. Are they dependent or not? Well, obviously not. Okay? If the time since the last train is small, then I'll have to wait longer. Actually, they are not only dependent, they are very strongly dependent. What is the sum of the two? If trains run once every 3 minutes, then the sum of the time since the last train at the time I'll have to wait for the next train is just exactly equal to 3. There is nothing random about it, okay? So, look at this. If we try to substitute these two random variables here, each of them has its variance. Actually, it will be the same number here and here because they're identically distributed. But the sum has no variance at all. It's 0 because it's not a random variable. It's just a number. There is nothing random about it. Okay? So, if we deal with dependent random variables, this formula doesn't work. Okay? But for the independent random variables, it's just like this. Okay. And well, I think I have a few minutes left, and I can at least start formulating this. You know what? Okay, I changed my decision. I'll talk about this theorem. I'll talk about this theorem next time. Just at this point, let me give you an informal formulation of the so-called central limit theorem. Well, when we started talking about the normal law, normal distribution law, we approached this question from binomial distribution. We said that when n, the parameter n in a binomial distribution goes to infinity, the distribution takes on a certain limiting form that does not change essentially when n increases further and further. Okay, so the sum of a great number of Bernoulli trials forms a normal distribution. Okay, this is how the normal distribution, the history of normal distribution started. But later on, a great discovery was made. Actually, it's the fundamental thing, which is the foundation of all statistics, by the way. It's this, that the sum of a large number of independent, identically distributed random variables is approximately normal. Okay, why is it so exciting? We started with saying that the normal distribution is the limiting case of binomial. But here we make a very large step forward. We say that a large number of identically distributed independent random variables of any law, any origin, finally gives us a normal distribution. Do you appreciate this? This explains why the normal distribution is so often encountered in nature. Okay? Because quite often what we observe is actually the sum of a great number of similar random variables. Whenever this is the case, we can expect to observe the normal random variable. And actually this is what happens in real life. Okay, thank you. See you next time.